Hi guys, and welcome to my channel. If you like what I'm doing and you want to see more, please subscribe. So I have started talking about gauge theories and gauge groups. I have talked about the standard model gauge group, SU3 times SU2 times U1, and in one of my latest videos I have showed you how you can build up the SU3 group generators. Today I will continue with the story on gauge theories, and I will specifically talk about SU5 group. I will show you how you can build up the generators of SU5 group, and I will talk about the algebra of SU5 group in detail, how it all started with Georgi Glashow in 1974, and a lot more. So let's start. In the world of so many theories and specific narrow point explications and postulations, there has been a need and strive for a theory that could and would tell the whole story. Now, ever since James Clerk Maxwell, physicists have been trying to unite separate theories into a greater one to cover it all. Grand unified theory is a term that is used to depict exactly the greater theory in physics. It is no longer a singular due to the fact that there are more than one grand unified theory. Nonetheless, here we will discuss one in particular, the theory based and explained on the gauge group SU5. Now, what about the unification? Unification means that three different coupling constants, alpha S, that stands for strong, now alpha 2 and alpha 3, where 2 stands for SU2 and 3 stands for SU3, would unify at some energy scale to the same value. Now, these scale-dependent coupling constants are calculated using the renormalization group equation that we can write in this form. Here in this equation, we can recognize that alpha with an index I is equal to gi squared over 4 pi, and it represents the coupling constants of SU2 or SU3, depending on whether I stands for 2 or 3. And mu is the energy scale at which these constants are to be calculated. Coefficients beta I are the beta function, where beta is equal to mu times partial of alpha I over partial mu, and Ng denotes the number of generations. Now, there is an interesting story how it all began. Howard Georgi and Sheldon Glashow published in 1974 an article with a bold introduction. SU5 is the gauge group of the world. It was a fair assumption, since the SU5 perfectly incorporates the first unification of SU2 and U1 with SU3. Now, rank of SU3 times SU2 times U1 is 4. Now, why 4? Well, here we have rank of 2, here we have rank of 1, and here we have rank 1. So overall, when we summarize it, we get number 4. And hence the smallest possible rank of unification group must be 4. Now, there are several groups that we could engage here, but only 2 of them, and only 2 of them are really interesting for us because only 2 of them have complex representations. Now, due to the fact that the generator of the electric charge in SU3 squared is traceless and requires the sum of all quark charges to vanish, SU5 was indeed a unique candidate for grand unified theory. Now, what about the Fermion sector? In order to find the right representation to arrange and unify all the fermions, we must organize their quantum numbers, and I show them here in this table. The idea is to assign them to specific representation and unify them according to their handedness. Hence, we use charge conjugates. Formula we apply to relate hypercharge, charge, and weak isospin is, of course, Q equals T3 plus Y. So we have hypercharge, charge, and weak isospin. What does that actually mean? Well, there are two options for construction of a multiplet of 5 states. That includes quarks and leptons. Now, when we write here number 5, it means that we must include 5 states. So we have one state here, second state here, and of course 3 here. So here we can have two possibilities. First one is to take down type quarks, and the second one is where we take the up type quarks. So what next? We must consider electric charge in order to determine the suitable multiplet. So we already stated that the formula we will be using is this one. So when we take the charge of the, let's say, first combination, that means that we have to summarize over all these states, all 5 of them. And when we take these down type quarks, and these are charge conjugates, that means that the charge of down type quark is -1/3, but since we have this charge conjugate, this will become plus. Hence we have 3 times 1/3. Now the charge of electron is of course -1, hence we have -1 here, and the charge of neutrino is of course 0, hence we have 0. So overall for this first combination we get 0. When it comes to the second one, we get that the charge is overall -1. Now, the idea here, as I already stated, was to determine which of 2 options among these 2, so this one or this one, gives for charge of Q value 0. This is due to the fact that we will assign 2 of the SU5 generators to Y and T3. And since both of them are traceless, therefore the Q must be traceless as well, because we already stated that Q is equal Y plus T3. Thus it follows that the right multiplet with both quarks and leptons looks like this. So we write this combination here. We have separated this multiplet in 2 parts. The first one with these down type quarks, charge conjugates of course, and here we have lepton part with electron and neutrino. Now, knowing 5 bar, because we have the little bar here as you can see, okay, knowing 5 bar, we can, by applying charge conjugation, find the fundamental representation, which is phi alpha, and it equals to 5 with some other states. We can write it right here, for example. So this was a phi alpha with the down index and phi alpha with the upper one, which is equal to 5 without the bar, because we're writing the fundamental representation, is equal to, now 3, 1, minus 1/3 plus 1, 2, 1/2. So we just take the opposite of these states here. Okay, what do we do next? We do this in order to find 10 more missing states, since in the standard model there are 15 Weyl fermions. Firstly, we will decompose the direct product of two fundamental representations to find reducible representations of SU5. So this is how we do that. So we multiply 5 by 5, and that is overall, of course, 25, which can be written as the sum of 10 and 15. Under the exchange of two indices that carry, since fundamental carries 1, so we know that this one carries just 1 alpha up, okay? 10 is anti-symmetric, and this one is symmetric one. If we write direct product of this one here, okay, in a form of irreducible representations, it will look like this. So we have reduced 10 and 15 to these two. Here we can distinguish that antisymmetric 10 is exactly the representation that contains 10 remaining fields. So this looks like that. Q equals, so it stands for quarks, up type quarks and down type quarks, so here in here, okay, and we get this. But beside that, we still have the charge conjugates that look like this. So once we have finished with the antisymmetric one, we can also write the next, therefore the antisymmetric would have this form, the overall one. Of course, we must not forget about the direct product here, the decomposition. We can write, for example, 5 times 5 bar gives us 1 in 24, which we will use afterwards. Now 5 times 5, we already have written this as 10 plus 15. Now 5 bar times 10 will give us 5 plus 45. 5 without bar times 10 will give us 40 plus 10 bar. Now 10 times 10 will give us 5 bar plus 45, 50, and 10 bar times 10 will give us 1 plus 24 plus 75. Now what about the gauge sector? After fundamental, symmetric, and anti-symmetric representations of SU5, because this is our topic today, the next one is adjoint representation. Now we have seen that we can find it using direct product 5 times 5 bar. So this is the first formula I have written in the direct decomposition of the direct product here, and we can see that this adjoint representation, which is 24, we can get in this way. So we have to multiply 5 and 5 bar, and we have to decompose it in order to get the exact states. Now if we read this carefully, we have 8 times 1, 8. 3 times 2, we get 6. 3 times 2, we get 6. 1 times 3, we get 3. And here we get 1. So overall here, we get 24 generators for SU5. 8 of 24 will be from SU3. So SU3 will give us, okay, 8 generators. Now we come to SU2, which will give us, okay, this we get 3 from here, and the 12th one, okay, just 1, we will get from U1 from standard model. So overall here we have 12 generators, but here we see that we must have 24 generators. Now, since the rank of SU5 is 4, so the rank is 4, 5 minus 1, 4, okay. The 4 diagonal generators will be 2 from SU3, okay, and T3 from SU2, okay, and from here it will be just Y. Now, these first 12 generators we can represent in this form. After that, we have to form the next one. Okay, so this is from L13 to L24. We already seen from here, for example, that we have used the Gell-Mann matrices in order to, let's say, expand them and to get these 12 generators. Now, we will be using this in order to form the next 12 generators. First of all, you can notice here that we use 1 and 1 in these places where they did not stand before. Also, you can recognize them in L17, okay, in the same manner. So we are just doing the expansion of these ones on different places in diagonal form, of course. And here as well, here as well. So L15, of course, and the remaining ones, we have 6 of them. They correspond the matrices with this I. So we have here, and we are doing the same expansion as we did with the ones. Okay, you can see the pattern, how it happens, the same story as it was with these ones. Okay, once we form these generators, we can make the V mu, where these generators can be represented with G12, G21, G13, etc. Now, these small letter G's, okay, like GI, that goes from 1, okay, to 8, they represent 8 gluons, while X, okay, the capitals X and Y's, they are vector gauge bosons. These are mediators of the proton decay, whose mass corresponds to the new energy scale of unification of 3 coupling constants. These new bosons convert quarks into leptons and vice versa. They can be expressed in terms of equivalent fermions. And these are their formulas. So it follows that they form an isospin doublet, carry color, and lepton quantum number. And you can see with these Feynman diagrams how they help to convert, for example, these quarks into quarks and leptons. So depending on whether we have as a final product a lepton which is charged one or neutral one, so let's say positron or neutrino, we can differentiate between X's and Y's. So with different products, in the end, we can say the difference. Now, what about the Higgs sector and symmetry breaking? The SU5 symmetry, we know that from before, okay, so SU5 is broken to SU3 times SU2 times U1. And this is done by specific Higgs field. the 12 new vector bosons, and these are X and Y's, they become massive after the first stage of spontaneous symmetry breaking of SU5, since standard model has 12 gauge bosons and SU5 has 24. Now the first stage happens at mass scale, okay, mu, that is approximately m of gut scale, which corresponds to 10 to 15 GeV. The second stage comes at the electroweak scale, okay, so now mu corresponds to 250 GeV when W, okay, and Z acquire their masses. Now the specific Higgs field needed for the first stage of symmetry breaking is the one with real scalars. And here these belong to 24 representation. So they belong to 24. We know from before that 5, okay, times 5 bar is equal to 24 plus 1. It follows that Higgs field, and we will denote it by capital Phi, okay, can be represented by 5 times 5 matrix. The idea is to have a Higgs field to give masses to X and Y gauge bosons and not to other fields at the moment. So we need to use Higgs field, okay, to give masses to X and Y, but at the moment when this Higgs field gives masses to X's and Y's, it cannot give masses to other fields. Since we know it must be 24 adjoint at SU5, okay, adjoint of SU5, it is Hermitian and it will transform as phi, okay, goes to this form. It is well known that Hermitian matrix can be put in diagonal form using the proper unitary matrix, and we can write it like this, okay, the same expression as we had before is equal to phi diagonal. Now, knowing that this matrix, okay, this one, is also traceless, there are several options here. So the first one is to have, let's say, AAA, now B, and the fifth term would be minus 3A minus B. Because it must be traceless, we have to have 0. So 3A's minus 3A 0, B minus B 0. The next option would be to have 2A's and minus 2A's, 2B's minus 2B's, etc. So we can play with this a little bit more. And this reads like diagonal 1 minus 1 and 3 zeros, or 1 1 minus 1 minus 1 0, etc. So we have different combinations here. But the question here is which of these 5 combinations is the realistic option? Now the only realistic option here is the third one, and that is the one here, okay, which corresponds to these values. So how does it look? We can write it in this 5 times 5 matrix with values 2, 2, 2, and minus 3 and minus 3. Now, what do we do with this one? We already written this as 5 times 5, but we have this V part. V stands for V equals to this V over square root of 30. However, this Higgs field cannot induce the second phase of SU5 symmetry breaking that would give mass to W and Z. This is because phi does not have a color singlet. and an isospin doublet necessary for vacuum expectation value of W and Z. Beside this phi, okay, S24 cannot couple and give mass to fermions, since fermions reside in either 5 bar or 10. And you can see here, so we can have these combinations, 5 bar times 5 bar, or 5 bar times 10, or 10 times 10. So these are only combinations where we have fermions. From these equations here, it follows that second stage symmetry breaking Higgs field must be 5 or 45, because these are for fermions, okay? And we can have either 5 or 45. Now the simplest version is to have Higgs to be 5. This version would have standard model Higgs H and an additional color triplet T. It looks like this. Since this 5H now can give mass to fermions, the mass giving Yukawa interaction would be of this form. So we would get up-type quarks in this form, 10 times 10 times 5H, so 5 of Higgs. Then the down-type quarks, we would get them from 5 bar times 10 times 5H with this asterisk. And we can see the following for electrons. Now the Lagrangian Yukawa part would look like this, where this Y5, okay, this part here, and Y10 are matrices in generation space, and epsilon 5 is 5-dimensional Levi-Civita tensor to contract all upper indices, and it can be represented in this form here. Now, to summarize it, the minimal SU5 has 2 Higgs fields. One for spontaneous symmetry breaking, 24H, so we can write it as this, 24H, that gives mass to vector gauge bosons, which are X and Y. And the other one, which is 5H, that is responsible for mass of standard model content. So this would be, in short, the representation of SU5 group, how we form the generators, how we obtain the spontaneous symmetry breaking with 2 Higgs fields, first one of 24 that is responsible for masses of X and Y's, and the second one, which is 5H, responsible for the other masses. I hope you like this video, and if you do, please subscribe for the next one in some specific SU5 models. So that will be all for today. See you in the next video.